This is the Redox and Electrochemistry practice exam review, and especially this is practice for your IA4 for this year. And yeah, this is going to be really long because there are 9 pages of practice questions, but nevertheless, we're going to start with number 1 on page 1. And so we start here with this question asking about the oxidation state of nitrogen in this compound, NH4Br. So keep in mind for compounds, the oxidation state in total has to equal out to 0. If you didn't know this by now, but you should probably get yourself familiar with table E. NH4 is a polyatomic ion with a charge of +1. So within this polyatomic ion, NH4 total has to equal to a charge of +1 because it's a polyatomic ion and not a compound. So I'm going to set up an equation here. +1 has to equal the sum of all the hydrogens and the nitrogen. So N is what we're looking for. And we have 4 hydrogens here. We already know that each hydrogen is going to be +1 each. You could easily look that up on the reference table, and most commonly hydrogen is +1 instead of -1. Okay, so you're going to get that +1 equals N plus 4, bring this to the other side, and you get that the charge of nitrogen will be -3, which is our answer here. Okay. Now, number 2, given the balanced equation representing a reaction, we're looking at the oxidation state change for chlorine. And so here we're looking from left to right. And let's focus on KCl. Because K being a group 1 metal, it will always be +1. Oops, I did this wrong. Which makes Cl -1. So let's cross off choice 1 and 4, because we see as it goes from the left side to the right side, it becomes a -1. Chlorine will become a -1, which leaves us with choice 2 and 3. Now we have to decide if it's +1 or +5, and that means we have to break down KClO3. K is always +1. That we know for sure. Oxygen is -2, but since we have 3 of them, there's -6, because each of them is going to be -2. Now, to balance it out, Cl has to somehow make things equal out to 0. So +1 and -6 make -5. So to balance that out with what we have already, Cl has to be +5. Which means it goes from a +5 all the way to -1. All right, number 3. What is the oxidation number of chromium in the chromate ion? Oh, CrO4 minus 2. So let's do it in a different color. Each oxygen is -2. Okay, so I did the work already. Each oxygen here has a charge of -2, but since we have 4 of them, it has a total of -8 here. Now, in order to make this entire thing add up to -2, I'm making chromium +6. So +6 minus 8 gets you -2, and that's their charge of chromium. Oops. Okay, so we're looking for the highest oxidation number of chlorine. Know that oxygen will always be -2, and sodium would be +1. So to balance that out, this chlorine has to be +1. In this case, this is going to be a -6. This is a +1. So it has to be a +5. +1 minus 4. This one's a +3. And so in this one, we have a -8. +1 to balance it out has to be +7, so it's going to be choice 1. Because look how we need to balance things out. To 0, each oxygen is a -2, so make sure you multiply accordingly, and Na is always +1. Okay, redox, we're always having some sort of electron exchange. So you're never changing protons, because if you change the number of protons, you're changing the element. You need to change the charge of the element, not change the element itself. And the only way we could do that is by changing the number of electrons. So electrons can only be exchanged. So the number of electrons loss always has to equal the number of electrons gained. So if someone gives up 2, someone else has to take those 2 electrons. So it has to be equaled out. All right, number 6, the chemical process in which electrons are gained by an atom or an ion is called, so electrons gained. I always say the phrase Leoger. Losing electrons gets you oxidation. Gaining electrons is reduction. Okay, so that's choice 4. Number 7, an oxidation reduction reaction involves the transfer of electrons. You're not transferring protons or sharing, that's for sure. And you're not sharing electrons either. Someone has to give up those electrons completely, and someone has to take it. So that's a transfer of electrons, not sharing. Okay, number 8, which half reaction correctly represents reduction? So we have to think gaining electrons. So someone has to gain, it has to appear on the left side, because it has to look like it's absorbing those electrons to become something else. Now we have to make sure these are done correctly. So we can cross off 3 and 4 because we need electrons on the left side of the equation. Now, which one shows a proper change in the charge? That'll be choice 1. Because choice 2 does not show it properly, because if you gain 3 electrons, you should be more negative, not positive, which is why it's choice 1 and not choice 2. Okay, when Pt2+ is reduced, so platinum, being reduced means you're gaining electrons. Okay, so you could cross off 1, cross off 4. So when you gain electrons, you become more negative in oxidation state. So you're decreasing. Sorry. So it's choice 3. Number 10. Okay, we have a balanced ionic equation. In this reaction, electrons are transferred from where? So we need to see who's doing what. So Al goes from positive 3 to 0. That's reducing. Whereas Mg here goes from 0 to 2+. Okay? So the one that loses electrons is Mg because it becomes more positive. And then Al3+ gains. So it always goes from whoever loses to whoever gains it. So it always goes from loses to gaining. So it's choice 4. Because these 2 on the left side are the ones that play. One is giving up, the other one's taking to become 2 new different substances on the right side. Okay? So you're always dealing with the ones on the left side. The ones on the right side, they kind of tell you what's becoming what, but they're not telling you who's doing what. Okay? Who's gaining and who's losing. They're only the products of either gaining or losing. All right, number 11. Compared to the total charge of the reactants, the total charge of the products is the same, conservation of charge. Okay, charge must always be conserved, just as mass and matter and everything else. Number 12, the oxidation number of a reducing agent. So agents are those that help the other process. So a reducing agent is the one that gets oxidized. By being oxidized, you help the reduction reaction. You're a reducing agent. So being reducing agent means you're being oxidized, so you're becoming more positive by losing electrons, and that's choice 2. Which ion is most easily reduced? So you need to check table J for number 13. So I'm going to pop it up in a bit. All right, so I popped up table J right here, and so when we're looking for something that's most easily reduced, you're the more, or not really more, you're the less active one over here on the metal side. So most active are the ones that get easily oxidized, and the ones that are least active are more easily reduced. So we're looking for the one that is towards the bottom, the most bottom one. So here we have Ca, we have Zn, we have Mg over here, and then we have Co over here. So the one that's the most bottom is CO, hence choice 2. Okay. And last but not least, on number 14 on this first page, which species acts as a reducing agent? So again, you're the one being oxidized, so you're losing electrons, becoming more positive. Losing electrons, more positive in charge. So looking here, iron goes from 2 plus to 0, so that's more negative, whereas zinc goes from 0 to 2 plus, that's more positive, so it's zinc. Not Zn2 plus, it's zinc, because it's the one losing electrons to be a reducing agent. You're helping someone else be reduced. So that's what it means to be an agent. Number 15 on page 2. In a redox reaction, the species reduced gains electrons. So gaining electrons, reduction. So when you're being reduced, you're the oxidizing agent because you're helping someone else be oxidized. By gaining electrons, you take those electrons from someone else that loses it, so you're an agent of someone losing, okay? If you could think of it that way. Number 16, a reducing agent will always gain electrons. No, sorry. Whoopsies. Reducing agent gets oxidized, so you're losing electrons. Number 17. Which half reaction represents the reduction that occurs? So first we need to identify who's being reduced and who's being oxidized. So Al here goes from 0 to 3 plus. From 0 to 3 plus. That's being oxidized. Whereas Cu goes from 2 plus to 0. That is being reduced. So we're looking for a Cu being reduced, so it has to gain electrons. So that's why it's choice 2, because it's gaining electrons to become Cu, and not the other way around. Okay, now over here. We're talking about Al going from 0 to Al3 plus by losing 3 electrons. And then Cu, 2 plus, has to gain 2 electrons to become Cu. So based on this, we're focusing on the left side. These are the species at play. Al here is the one that's losing electrons. So each Al loses 3 electrons. So that's choice 4, while each Cu2 plus has to gain 2 electrons. Okay. Number 19, which reaction occurs spontaneously? So this requires us to look at table J. All right, number 19, I pulled up table J again because we need to see who reacts more spontaneously. So spontaneous reactions, oopsie daisies. Let me pick another color while I'm at it. Let's go for red. Which reaction occurs spontaneously? So when we say spontaneously, we mean the free element, the one that starts off by itself, has to be more active. Okay. So when we say the free element, we're looking at these guys on the left side. Okay. These guys are the free elements because they're by themselves. Has to be more active than the elements they're replacing. So look here. They come in, they swoop in, they break up these couples, and they take them for themselves. Look at chlorine and iodine being couple breakers. They take Na for themselves. So we're looking at whether or not chlorine or iodine are more active than the ones they're replacing, bromine and fluorine. So we could say that fluorine is the most active of these guys, these nonmetals. So anything trying to replace fluorine has to occur non-spontaneously. So these guys are non-spontaneous because they're trying to replace fluorine, and fluorine is the most active. So if you're below fluorine and you're trying to replace it, you're going to have to force it with a lot of energy. Now let's see. Chlorine and bromine. Let's look at choice 1. Chlorine is trying to replace bromine. So let's see. Chlorine is over bromine. It's more active than bromine. So that is definitely spontaneous. But let's just verify for choice 4. Iodine and bromine. Bromine is over iodine. Iodine is less active than bromine. So since iodine is trying to replace a more active bromine, that has to require extra energy, making that one non-spontaneous, which is why it's definitely choice 1. Okay, number 20. Which metal is more active than H2? So again, we're looking at table J. Here is H2. So we're looking for any one of these guys that are above H2. So Cu is below, Ag is below, Au is below, and Pb is the one right above it. So it's more active. Now number 21. Which type of reaction is occurring when a metal undergoes corrosion? So if you weren't paying attention for the past few weeks, then clearly you will get this question wrong, because all we've been talking about is oxidation reduction. We're not talking about saponification, we're not talking about neutralization, and we're not talking about polymerization. 2 of these we haven't even learned about, okay? So those we'll learn in the next organic chemistry unit, but right now we've been talking about oxidation reduction, and that's our clear answer here. Otherwise, you're an idiot who has been going to sleep for the past 2 weeks. Anyway, moving on. Here we have some free response questions dealing with electrochemical cells. So numbers 71 to 73 here feature a Voltaic cell with a balanced ionic equation given. So 71 is asking, what is the total number of moles of electrons needed to completely reduce 6 moles of Ni2 plus ions? So first of all, let's look at Ni. Going from Ni2 plus to Ni. So it needs to gain 2 electrons for this to even happen. So for every mole, 1 mole of Ni2, then you have to gain 2 electrons. So let's say we multiply this by 6, because we need 6 Ni. Okay, so this becomes now 6 Ni2 plus. If we have 6 moles of Ni2 plus ions, then we had to get 12 moles of electrons to yield 12 mole, sorry, not 12, it's supposed to be 6. Okay, so it's saying for every 1 Ni2 plus, we need 2 electrons. So what happens if we have 6? So then we have to multiply it up by 6, and we get 12 moles of electrons total. Sorry. All right, number 72, identify one metal that is more easily oxidized than Mg. So when we say more easily oxidized, we're going to say more active. Okay, so let me add table J back into the fray. Oopsies. Is this still recording while I'm in the midst of adding something? Oh, yes, it is. Voila, it's back. Okay, let's bring it over here. So we're looking for Mg. Mg is over, nope. Go back. Mg is over here, so we're looking for something above it. Name any one of these that are above it. If you want to play it safe, always go with Li for the one that's easily the most active. But you can also talk about rubidium, potassium, cesium, barium, strontium, calcium, and sodium. Okay. Now, number 73, explain the function of the salt bridge in a voltaic cell. So here in a voltaic cell, electrons are definitely flowing from the anode to the cathode. So electrons are flowing through the wires, and so something here has to complete the circuit. So that's the salt bridge. It completes the circuit by allowing ions to pass through from one half cell to the next. So while electrons are flowing through here, ions are flowing the other way through the salt bridge. So it allows the transport of ions to neutralize the cells. So it allows the transfer of ions between the half cells. That's all you need to say. Okay, now number 23, 24, and 45. Let's start with 23. Which change in oxidation number indicates oxidation? So we're losing electrons, become more positive. And that is choice 1. Number 24. As the reaction takes place, there's a transfer of electrons, absolutely electrons, not protons. Now, who is losing what? Cr gains, Al loses, okay? Because Al goes from 0 to +3, so it loses electrons. So it's going to go from Al, and Cr3 plus here is the one gaining them. So it has to go from Al to Cr, from whoever loses to the gainer. Number 45, which half reaction can occur at the anode in the voltaic cell? So this you have to know as oxidation because of the phrase I taught you guys, anox. At the anode, oxidation occurs. So anode oxidation. So let's cross off 1 and 2 because they show the electrons being gained on the left side. So we're looking for electrons being lost on the right side. And we need to see which of these has it down properly. And so we're going to go with choice 3. So here, it's usually the free elements are the ones that are losing electrons in a voltaic cell. It's the free elements that are the spontaneous ones losing, okay? So they're the ones that lose the electrons, whereas ions don't really necessarily lose electrons. They're usually the ones that gain the electrons instead for voltaic cells, okay? So usually, okay, typically free elements lose electrons, especially in the case of metals. For the nonmetals, they gain electrons, whereas the ions gain those electrons instead. Okay, usually in the case of metals, all right? Okay, when the switch is closed, which electron will attract the sodium ions? So the cathode is where reduction occurs, whereas the positive electrode, the anode, is where oxidation occurs for this electrolytic cell. Okay, and so here we can see that sodium ions go from Na plus to Na, so it's the one getting reduced. So Na plus are gonna travel to the cathode. Because remember that electrons always flow from anode to cathode. Okay, so the electrons are going to travel to the cathode, and as a result, they're going to attract the Na plus ions to make solid Na. Okay, so electrons will crowd around on this guy. Let me use a different color. So these electrons are going to crowd up on this cathode and attract the Na plus ions to solidify it, and that's how you make solid sodium from this electrolytic cell. Number 75, what is the purpose of the battery in this electrolytic cell? So electrolytic cells are non-spontaneous to begin with. So you're going to need electrical energy to jumpstart a chemical reaction. So it needs electrical energy to jumpstart it. So that's why a battery is there. Provides electrical energy to start a non-spontaneous reaction. Okay, number 76. Write the balanced half reaction for the reduction that occurs in the electrolytic cell. So as I mentioned before, Na plus is the one that's gaining electrons to become solid Na. So let's write a balanced half reaction. So if we look in the original reaction, we have two Nas. We have 2 Na plus has to gain 2 electrons because each Na needs 1 electron. And so since we have 2 of them, we need 2 to yield 2 Na. Does that make sense so far? But that's the answer. Number 26. Where does oxidation occur in an electrochemical cell? Anox, so it's at the anode in both cells. So that's what's in common with both voltaic and electrolytic, is that anodes, it's anox and red cat, all right? Anode oxidation, reduction at the cathode, and it's the same for both. Number 49, which equation represents the oxidation half reaction? So oxidation, losing electrons. So who's losing electrons here? It's zinc for sure. Zinc goes from 0 to 2 plus, and it's choice 2. Alright, and we're just about halfway through. Oxidation reduction reactions occur because of the competition between particles for electrons. It's always electrons. Number 2, which type of reaction is occurring when a metal undergoes corrosion? I believe we did this already, and that's choice 3. Number 3, which change in oxidation number represents reduction? So reduction is gaining electrons to become more negative. So you have to become more negative in charge, and that is choice 1. Which represents a redox reaction? So typically you're looking for synthesis reactions, decomposition reactions, or single replacement. Those are the typical common types of redox reactions where they occur. So number 1 is double replacement. That's definitely not. And so is 3. So we're down to choice 2 and choice 4. Now, the long way of figuring out whether it's choice 2 or choice 4 is by assigning oxidation states to every single element in both reactions to see if one changes and to see if 2 different elements change oxidation states. Because you need to show that one gives up electrons and the other one takes it. But this shortcut I'm going to show you is to just look out for a free element. So if you see here in choice 2, you have KClO3 decomposing into KCl and O2. So O2 here is our free element. And most likely, with a free element, you go to 0, whereas here on this other side, you start out with a charge and you go to 0. All right, so free elements always have a charge of 0, and that when it's bonded with another element, it has a charge. So in choice 2, you see that oxygen here goes from a charge to 0. So it definitely shows a change in oxidation state. And that is the case. That's the answer. Choice 2. So you most likely look for a single replacement. That's the most obvious, most common answer. But in case you don't have any of those 3, then you look for a reaction that has a free element by itself. Okay? Number 5. As a reaction occurs, what happens to copper? So here we see copper is a free element. It has a charge of 0. And then when it goes to the other side, it bonds with another one and it becomes an ion. Okay? So in this case, NO3 has a charge of -1 each, but since we have 2 of them, it's a total of -2. To balance it out, Cu has to be +2. So Cu goes from an oxidation state of 0 to +2. And so it loses electrons. 2 electrons. It undergoes oxidation, and its oxidation number increases because it loses electrons to become more positive. Number 6. In which substance does hydrogen have an oxidation number of 0? So that's only when it's a free element by itself. Number 7. Which changes occur when Pt2+ is reduced? So reduced meaning you're gaining electrons and you become more negative. So you gain electrons and your oxidation number increases. Alright, number 8. The magnesium is the what kind of agent and what is it doing? So magnesium here goes from a charge of 0 to +2, whereas 0 goes from 0 to -2. Okay, so magnesium is being oxidized. So we can cross out 4 and 1. And when you're being oxidized, you're the agent of the other process. Choice 3. Number 9. Which half reaction equation represents the reduction of an iron 2 ion? Okay, reduction meaning you're gaining electrons. Iron 2 is Fe2+. So it gains electrons to become Fe. And that's choice 1. Number 10. Which balanced equation represents a redox reaction? Okay, so here we're looking for for either synthesis, decomposition, and single replacement. Now, choice 1 is not necessarily decomposition. It's just a compound breaking up into its ions. And it's the same thing with choice 3. It's two ions coming together to make the compound. So they still maintain the same charge. Choice 2 is double replacement, so that is not the case. And instead it's choice 4. Because here you see a compound breaking down further into its components. And Cl2 is a free element, and that's a key thing to look out for. Okay, the free element for redox reactions. That's a common component of it. Now, number 11 is asking us to reference table J, so I'm going to pull that up again. Okay, reference table J is asking us for number 11, which reaction will not occur under standard conditions? So will not occur, so we're talking about non-spontaneous. So that means the free element here has to be the less active one. So non-spontaneous means the free element is the less active one. So here, we're seeing that each of these guys are replacing H2. So we're looking for something that is below H2. So we see that SN is above H2. Cu is below it, so that's a possible choice. Ba is above, and so is Mg. So we're looking at Cu because it's the only one that's below H2 and less active. So non-spontaneous means the less active one is the free element. Okay. Number 12. Which half reaction shows conservation of charge? So that means the total charge on the left side has to equal the total charge on the right side. So number 1 is not correct. Number 2 is correct. Number 3 is not. And number 4 is also not correct. So the only one that is correct is choice 2. Here we have an ion gaining electrons. It become 0, and it's being reduced, so it's conservation of charge to balance it out to 0. So in terms of ionic equations being balanced, we need to make sure the number of electrons, okay, number of electrons lost equals number of electrons gained. Okay, so we have to go through each of these choice by choice. So Fe3 plus going to Fe2 plus. So that's one electron being exchanged there. So this here is 1 electron, but this here is 3 electrons. So that's not balanced. Number 2, that's 1 electron. That needs 9 electrons. So each Al needs 3 electrons, but then since there are 3 of them, there's going to be 9 required, so that's not balanced either. Choice 3. Here we have 3 Fe, 3 plus going to 3 Fe2 plus, so that's 3 electrons, and 1 Al only requires 3 electrons. So that is true, that is balanced. But let's check with choice 4. Here we have 3 Fe, 3 plus, so that's going to need 3 electrons. But here we have Al going to 3 Al, 3 plus. That's not balanced at all, because you could even see here that you don't even have the same amount of Als on both sides of the equation. So you got to make sure that's also balanced in terms of atoms too. So that's why it's choice 3. Number 14. Which simple oxidation reduction reaction is not correctly balanced? Okay, so here you need to make sure that the number of electrons are also equally exchanged. So going from 2I minus to I2 0, you need 2 electrons to go to this section, but here going 1 Fe3 plus, you need 1 electron, so that's not balanced. And that's actually our answer, to be honest, but let's go check with the others. Sn here needs 2 electrons to lose, and this one gains those 2 electrons, so that's balanced. Here it loses 2 electrons, it gains those same 2 electrons, so that's good. Here it needs to lose 2 electrons, and here it gains those 2 electrons, okay? So that's why choice 1 is the answer. It's not correctly balanced. This one only needs 1 electron, and this needs 2 electrons to be given up, and this one only takes 1, so it's not completely balanced out. You need the same electrons lost equaling the number of electrons gained. All right, now number 15. We're in a tricky section here. When this equation is balanced, both Fe3 plus and Fe have a coefficient of what? So let's see. Okay. So Fe3 plus has to gain 3 electrons to become Fe. Now we have 3 Mg, and it has to lose electrons. So each Mg loses 2 electrons, but since we have 3 of them, it has to lose 6 electrons total. Because each here loses 2. But since we have 3 of them, we multiply by 3 to get 6. Now, because these two aren't exactly balanced out, we need to make sure that the same number of electrons are being exchanged between both reactions. So in order to make this equal out to 6 electrons, we double this entire thing. Okay? And so all of these ions, Fe's, are going to have a coefficient of 2. Because the total of how many electrons are being transferred? 6. We got to make sure that there's the same number of electrons here. So if we multiply this first equation by 2, we get 2Fe, 3 plus 6 electrons, yielding 2Fe, so that both of these things are equal and balanced out right here. Number 16, which energy conversion must occur in an operating electrolytic cell? So electrolytic, you're thinking you need electrical cut things. So it requires electrical energy to convert to chemical energy. Choice 2. Voltaic is the other way. Okay? It takes chemical energy to create electrical energy. Number 17, what occurs when the switch is closed? So that means it turns on. Here you need to look at table J. And table J will tell you that zinc here is more active than Cu. So zinc here is the anode because it's more likely to be oxidized. And this one's more likely to be reduced. And so that makes copper the cathode. So electrons will flow definitely, and one of them will get oxidized and one again will reduce. So zinc is the anode, so that's oxidation. And cathode is reduction, so it's definitely not choice 2 or 3. So it's definitely electron flow. They always flow from anode to cathode. Fat cat, in case you guys needed a phrase to remember. Fat cat. From anode to cathode. You could also think about it that anode oxidation, they lose electrons and they have to go somewhere. They go to the one getting reduced because they're the ones that gain electrons. So it always goes from anode to cathode, and that is choice 1. Number 18. Here we have an electrolytic cell because here we have a metal trying to coat up a key. And so which statement best describes the key? The key or the object in play will always be the cathode because you're trying to get electrons here. So notice how the electrons are flowing from silver to key. So it's always from anode to cathode regardless of cell. So the cathode here definitely acts as the key acts as a cathode. Now what sign is it? So keep in mind here, electrons flow to the positive end of the source and out from the negative end. So the cathode here is definitely on the negative end of things. So that's why it's negative. And it's also, if you think about it, it's the opposite of what we usually think. For the voltaic cells, cathodes are positive and anodes are negative. But for electrolytic cells, it's the opposite. Okay. for electrolytic. Okay, number 19. Which statement describes where the oxidation reduction half reactions occur in an operating electrochemical cell? So anox and red cat. At the anode, oxidation occurs and reduction occurs at the cathode. So that's choice 1, and that's true for both types of cells. Number 20. Write a balanced half reaction equation for the reduction of iron ions in iron 3 oxide to iron atoms. That's a mouthful of words that all look the same right here. I mean, how can you get that confused? They look all the same. I just look at it as ions, 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 ions. Anyway, so iron ions and iron 3 oxide to iron atoms. So iron 3 oxide is this. So this is really iron 3, and it's going to Fe. So it's Fe plus 3, and it needs to go to Fe 0. So in that case, it's gaining electrons. And how many? It needs to gain 3. So that's our answer for this one. Remember that this Roman numeral tells you the kind of oxidation state, the positive state. So it's iron 3, iron plus 3. That's it. Number 21, identify the component required for the electrolysis of molten NaCl that is missing from the cell diagram. So what missing component? It's a battery. So you could say a battery or voltage source or energy source. Okay. Almost done, guys. Okay, here we have an voltaic cell, sorry. Number 22, state in terms of energy why this cell is a voltaic cell. So here we're converting chemical energy from this chemical reaction into electrical energy, which is being measured in the voltmeter. Well, measures voltage, really. And voltage is almost like electrical energy, but not really. Because I'd rather not go into the heavy physics details of what voltage is when thinking at the atomic level. But anyway, I digress. Number 23. Write a balanced half reaction equation for the oxidation that occurs when the switch is closed. So when the switch is closed, the reaction occurs, and we're looking at oxidation. So we're looking at who loses electrons. So Al goes from 0 to plus 3. So that is the one that's being oxidized. So let me do a different color. Let's do blue. So it does Al to 2Al3 plus. Each Al loses 3 electrons, but since we have 2 of them, we have to double it. So that's 6 electrons. Each Al loses 3, but since we have 2, we double it. And 24, explain the function of the salt bridge. It transports ions between the half cells. Because otherwise we're going to have one side become 2 negative from all these electrons going through. So this would be 2 negative, and this would become 2 positive. So to neutralize it, we have ions flowing from this side to going into this side to balance it out. So electrons go here, ions go here. And finally, 26 on the very last page, state the direction of the flow of electrons between the electrodes in this cell. Okay, so simply put, you could just say it always goes from anode to cathode. Oh, actually, since we need to actually say in this particular cell, magnesium acts as the anode, iron acts as the cathode. So it goes from the anode, the magnesium, to the cathode of iron. So magnesium to iron or anode to cathode. Number 26, explain in terms of reactivity why magnesium is preferred over zinc to protect the underground iron pipes. Okay, so we need to explain in terms of reactivity. So we should think about table J, our best friend. Where's table J? Hello? There we go. Okay, So we need to explain in terms of reactivity. Magnesium and zinc. Magnesium's here and zinc is over here. Magnesium is more active than zinc. It is more reactive than zinc. And that's all you need to say. You don't need to get into further detail. You just need to explain in terms of reactivity. And that's all. You need to mention reactivity and mention both magnesium and zinc. Magnesium is more reactive than zinc. And that's it. And we're finally done. Alright, that was a long video. I bet this went for over half an hour. But I hope this wasn't a waste of your time. You should review. And try not to stress too much, guys. I mean, it's the final IA. I mean, there are other ways to bring up your grade afterwards. Test corrections. But nevertheless, it's always good to learn from your mistakes, even if you fail. Best of luck, guys. Study hard. Don't think too hard.